What's going on, everyone? I hope everyone's well. Today, we'll be looking at the second part of question 34, the quantum to quark section of the 2017 HSC Physics paper, and we'll be learning about the hydrogen emission spectrum, what Bohr's postulates mean, and why we bother studying anything about protons and neutrons. Okay, let's get started. So question C says, the diagrams show features of the hydrogen emission spectrum, and it's a 4-mark question. We're first presented with a diagram of the hydrogen emission spectrum in the visible light, 656 nanometers to 410, so that's red light to blue light. And then we're shown the different series of light, the Balmer series, Lyman series, and Paschen series of the hydrogen emission spectrum. So all the different types of light that the hydrogen atom, or the hydrogen spectrum can have, basically. So it can have the visible light, ultraviolet light, and infrared light. So the question says, with reference to Bohr's postulates, explain how the line at 434 nanometers in the hydrogen emission spectrum is produced. Support your answer with calculations. So the first thing I've done here is I've written out Bohr's postulates. Now you don't have to do this for your answer. I've just put this here so I can use it as a talking point, and then you're aware of what I'm talking about when I talk about it in my answer. So the first one says, electrons in an atom exist in stationary states in which they possess an unexplainable stability. Now, just to clarify, it's no longer unexplainable, but when Bohr did it, he didn't get why they were in stationary states and why they were fixed in these fixed orbits. Bohr's second postulate, a transition between two stationary states will result in the absorption or emission of electromagnetic radiation, which is a photon, and that the energy gap, delta E, is equal to just the difference in energies between the two energy levels, E1 and E2, and that will equal, and the difference in that energy will equal the energy of the photon, which is given by the formula HF. And finally, his third postulate is angular momentum of the electron is quantized. And we don't need to know much about that in this case, but there it is, if you need to know it. So the question's asking, with reference to Bohr's postulates, explain how the line at 434 nanometers in the hydrogen emission spectrum is produced. So that's this line here. Cool. First I'll go through my answer and I'll explain what's going on. So, Bohr's postulates state that the electrons remain at certain fixed energy levels unless they jump into a higher or lower energy level. That's his first postulate. His second postulate states that if an electron jumps from a higher energy level to a lower energy level, then a photon will be emitted with the same energy as the energy difference between the two energy levels. If blue light of 434 nanometers is emitted as an electron jumps down, then it is jumping from the energy level n equals 5 to the level n equals 2, which can be seen in the diagram. So I'll show you how we got to that. Let's move that. Okay, so we can see in the hydrogen emission spectrum that we've got 4 lines in the visible spectrum that are emitted between 656 and 410. And if we look over here at our lower diagram, in the Balmer series, that's this one here, let's look at that, we can see there's 4 lines there. And we can see, and what those arrows are indicating is that there's electrons jumping between energy levels, and they're all jumping down. In the Balmer series, they're all jumping down to the n equals 2 energy level. That's what we can see. We can see that they jump down from n equals 6 to n equals 2, n equals 5 to n equals 2, and so on. Now, there's obviously a bigger energy difference between n equals 6 and n equals 2 than between n equals 3 and n equals 2. The higher the energy level, the bigger the energy difference. That's pretty obvious in this case. Now, what you may not be aware of, but hopefully you are, is that blue light is more energetic than red light. So, we can see that 434 nanometers, it's in the blue part of the spectrum, and it's the second most energetic line, basically. So if we refer to this Balmer series, well, we can see that the second biggest energy gap is going to correspond to that 434 nanometers, and that means that the electron is jumping down from the n equals 5 energy level to the n equals 2 energy level. That's how we get that that's how I wrote that second paragraph. That's how I get that information straight away without doing any calculations. But we can also do it with calculations. Cool. So we've explained the answer, referring to the diagram. Now we'll support our answer with calculations. So the information we've got is, so we don't actually know that it comes from n equals 5 yet. We have to calculate that. But we do know that the wavelength is 434 nanometers. Now, hopefully everyone's aware that 1 nanometer is 1 times 10 to the minus 9 meters. So we're going to convert that. So that equals 434 times 10 to the minus 9 meters, which equals 4.34 times 10 to the minus 7 meters. Now, the equation I'm going to use here is going to be the Rydberg equation, which is 1 over r equals, oh, no it's not, started wrong straight away, so 1 over lambda, 1 over the wavelength equals r outside of 1 over an f, couldn't remember, an f squared minus 1 over ni squared. And that's our equation that we're going to need to use. Now, lambda is just the wavelength. R is the Rydberg constant, which is R equals 1.097 times 10 to the 7 meters, or inverse meters. NF is the final energy level, and NI is the initial energy level. Now, since we're emitting energy, we're going from a higher to a lower. So the initial energy level, which is the first one, is unknown. That's what we don't know. But we know the final energy level is 2, since we're in the Balmer series. And now we're left with just one unknown, but we have to manipulate our equation to make Ni the subject of our equation. So the first thing I'll do, so I need to get to Ni, which is the subject, which I want to make the subject of my equation. The first thing I'm going to do is I'm going to move the Rydberg constant to the other side of the equation. And I'll do that by dividing both sides by r. So I get 1 over lambda r equals 1 on nf squared, I don't need my brackets anymore, minus 1 on ni squared. Cool. Now, I want to make ni the subject of my equation. That means I need to get it on its own. What I will do is I will move 1 over lambda r over to this side of the equation. So I'll subtract 1 over lambda r. And I need to move 1 over ni to this side of the equation. So it becomes plus 1 over ni squared on both sides. So I get 1 over ni squared equals 1 over nf squared minus 1 over lambda r. Cool. Now I'm ready to start substituting numbers. Could do more manipulation, but I'm just going to do it with the numbers first. So I'm interested in finding 1 over ni squared. I start substituting my numbers. Nf equals 2, so I get 1 over 2 squared. And I get 1 over lambda r, which I will write out like this. So that's 1.097 times 10 to the 7 meters inverse times 4.34 times 10 to the minus 7 meters. You don't really need to write your units in there, but I like to sometimes. And we can see that those units will cancel, so that's good. And that'll give me 1 over 4 minus that. And just because I've done this before, I don't know, I did this previously I should say, is that I know the answer is 0.3996. So if you plug that number into your calculator, that's what you'll get. And we're saying that 1 over ni squared equals 0.3996. And it's unitless. Now, we need to get ni. So the first thing we need to do is we need to get ni squared. So that means we're going to flip this equation. So ni will be on top of that fraction. Now, if what we do to one side, we have to do to other. We have to do the other. We should remember that every number can be written as just being over 1. So 0.3996 is the same as 0.3996 over 1. So that's also a fraction now. We've put it as a fraction. And if we flip one fraction, we have to flip the other fraction on the other side of the equation. So now I get ni squared over 1 equals 1 over 0.3996. So that means if I just put ni, so now I've got ni squared is equal to 1 over that. And if I need to find ni, well, I'll take the square root of both sides, and I find that ni squared equals 25. If I put that into my calculator, 1 divided by 0.3996. So ni squared is 25, and then finally ni equals 5 by taking the square root of both sides. Not too hard. That's basically it. So ni equals 5, and that confirms what we said here, where n equals 5. So we've explained it, we've supported our answer with calculations. That's our 4-mark question. Cool. So question D, part 1, says, how were the stable electron orbits in the Bohr model of the atom incompatible with a prediction of classical physics? 2-mark question. According to classical physics, the orbits of the electrons at each energy level or shell should result in the emission of electromagnetic radiation, and the electrons should fall towards the nucleus. Bohr's first postulate states that they remain in these states without losing energy, which breaks the rules of classical physics. So he said, this is what we observe. Not too sure why, but that's still his postulate. But we answer it in the next one. So part 2 says, how did de Broglie and Davisson and Germer contribute to the modification of the Bohr model of the atom? So that's a 3-mark question. So, de Broglie proposed a reason for the stationary states in Bohr's first postulate, which was the orbits of the electrons around the nucleus are akin to a standing wave. He proposed that all matter has wave properties, and stated that the wavelength can be calculated from the equation lambda equals h over mv. And then Davisson and Germer then went on to test this by producing interference patterns from the scattering of electrons off a heated nickel crystal, and observed that the wavelength of the patterns could be seen using de Broglie's equation. Awesome. So, the way it works, if we want to think about it, so Bohr came up with his postulates, but couldn't explain the first one. Couldn't explain why it happened. De Broglie came along and said, well, we can think of the same way we can think of particles, the same way we can think of light as having matter properties, where, i.e. photons. So we never had the thought of photons before Max Planck, basically, and Einstein. But we said, so light can have the same some of the properties of matter, which is like behaving like a photon. And then finally de Broglie came along and said, well, what if matter can behave like a wave? And he said every particle, basically every particle has its own, can be represented by its own standing wave, which isn't losing any energy. And that was why these electrons are losing energy, and that's why they're staying in these fixed electron orbits. And then Davisson and Germer came along and proved and supported de Broglie's theory using this equation with the experimentation, basically. So that's it. Part 2, 3-mark question. We've got de Broglie and we've got Davisson and Germer. Cool. Question E. So, explain how the properties of protons and neutrons contribute to their uses as tools for investigating matter. And this is basically where all this sort of stuff becomes useful. So, it's a 6-mark question, and it's an explain question. Now, I've got roughly equal proportions of stuff for protons and neutrons, or like equal amounts of explanation for the protons and the neutrons. And in this example, I believe I've got 6 sentences. So 1 sentence per mark, basically. Not necessarily exactly that. It doesn't have to be 1 sentence per mark, but that's just how it's probably going to work out for this answer. Okay. So, the electric charge of protons allows them to be used in particle accelerators to smash together at very high velocities and improve our understanding of the standard model of particle physics. Smashing together protons like this temporarily creates particles that sometimes exist for less than a nanosecond. The protons have to be smashed together at such high speeds to create other extremely high energy particles. So this couldn't happen unless those protons had an electric charge. They're charged, or they're run by these big potential differences that are created by these big electromagnets in these big circular parts like the Large Hadron Collider under Switzerland. And these protons are accelerated over very large distances, so 27 kilometers for this case. They're smashed together at these very high speeds, close to the speed of light. These huge energies are then used to create particles with very, very high energies, and they don't exist for very long. That's one of the examples of protons being used for stuff, to investigate matter. Neutrons, on the other hand, are neutrally charged, so they don't interact with any electric fields. And they're better able to interact with materials since they are not repelled by the Coulomb force and can get much closer. They can get right into a nucleus and examine it and see what's going on. Their magnetic moment can tell us much about magnetic materials. And the de Broglie wavelength of a neutron, which is relatively small compared to an electron, allows them to tell us much about the atomic lattice without causing destruction by examining the diffraction patterns as they scatter away. This is commonly used today in the production of new materials, especially nanoparticles. Okay, so we've given a pretty thorough answer for both protons and neutrons, and we've explained how those properties are being used to investigate matter. So we referred to their properties, and we referred to their uses for investigating matter. So I made sure to hit all those sort of things when I was thinking about my answer. Okay guys, that's it. That's finishing off question 34 of the 2017 HSC Physics paper, and this might be the last video I'll do for this paper. I might re-record some of my earlier ones because they weren't in great. They're not great quality. You know, my voice is a bit quiet in them, and the aspect ratio is off for one of them as well. So I will remake some of those videos, those earlier ones for this paper. Guys, if you like this video, please give it a thumbs up. And if you want to see more of this content or some different content that you think I'd be able to, that you think you'd like to see me produce, just leave a comment in the section below. So yeah, that'd be great. Have a good day, guys.